Hi everyone, my name is Professor Prof Pulle, and today we're going to talk about drones, control of electrical drones. Now a drone is nothing else than a PM synchronous machine, as you see here. And here's another one, and they're both what they call outrunners. And they are essentially, can be driven exactly the same way as any other PM sync machine using that inverter, which is the one you see here. In this case, we're going to control it sensorless. So it's going to be talking about sensorless field oriented control using Altair Embed. So that's basically the steps we're going to see: torque control and speed control perhaps, and lifetime. And that's it. So the first step we do is to look at the setup, which means we have the hardware, which is the drone, which is the T motor unit here. We have the propeller connected up 15-inch. We have the motor mount, which is from my colleague, University of Sharjah, Professor Rashed Dawadi. He has developed this setup. He uses that. And we have the text image launch pad, which is the one down here. And we have the converter, which is the drive, the boost drive 8301. Up to 10 amps capability, 24 volts. We have a 24 volt supply, 4 amps is sufficient for this application. The software is Altair Embed, Personal Edition, 64-bit. And the files you'll need are two files. One is for compiling the file which I've developed, and the other one will run it, which we'll see here. So that's the step we're going to take. And we'll now move on to the actual file. And the file we are going to run now, this is the compile file we're going to have to create. If we look inside that, there's a main motor controller. If we look inside that, you'll see the drive controller and the ADC PWM unit. That unit measures nothing else than the voltages, low pass filtered voltages, the 3-phase currents, and the DC bus voltages. And they are basically Clark converted to alpha beta coordinates in currents. Right, and looking inside this unit, we see here the current controller. And the current controller will have as input, in this case, we can control the D-axis. So let's go back to the presentation again. And that is the one here. And in that case, so what we are going to control in this case is looking for the D-axis, and we're looking for the VM flux that is found by measuring the bus volt, by the terminal voltage, and the current vector, which is shown here in 90 degrees to the flux, because that's the optimum torque normally for field oriented control. So we need to understand what the volts across the inductance is. That is expressed in terms of the EMF amplitude, the current vector, and the short circuit current of that machine. For this machine, it's 36 amps, so 6 times typically the currents we're seeing here, around 8 amps. So this component is relatively small. The volts across the resistance is simply IS times resistance, and that is then subtracted also, so both of these are subtracted. We find the EMF, and the EMF is then used by the FAST algorithm, and I'm one of the developers of that algorithm, and which is so I know quite well how that works, and we will use it in our books for effectively all of the all types of machines. So in this case, FAST takes the EMF and finds the flux vector. That angle is basically then used in the FAST algorithm. That angle is used by the current controller. It also produces the flux and the speed. Torque is not necessary because flux and quality current will give you the torque. Right, so that's the basic step of it. Back to the compile. And the compile mode in this case here will be up here. And there you see it. There's the InstaSpin fast algorithm. It has the flux and it has the angle coming out. We also estimate resistance because resistance is critical at low speeds. And the angle when FRC is active is used for the current controller. So that, in a nutshell, is what we are trying to do here. Moving on now to the next step, which is the run version. The run version, after compiling the file, we have an out file here, which we've already compiled, and that is basically used here. So now the next step is to do first mode of operation, open loop current control. So when we do open loop current control, FOC is off, speed loop is off, and we have no measurement resistance. And if we download the file, as we do now, we download the file, and we shall see here, we see indeed the bus voltage, 24 volts in this case. So if we hit the button now, very gently, and here we see open loop current control. Now that is the first check. And by doing that, the fast algorithm should check it. Now we see a speed of, we've set the reference speed at 94, and fast is tracking it. And we're seeing here a shaft speed of 94, and the flux is 2.3 milliwebers. So that is the first step. So it works, and here we see the current vector, rotating current vector. There's no torque, of course, measurements, and no, this is not working as yet. Here we see the DQ, and we'll zoom in that shortly, and that is showing you the D-axis and the current in this case. All right, so that's the first check. The next step is to move FOC torque control. That's what we'll do now. So we'll switch it off, and we'll set ID to 0, and we will do that. And now we're going to go FOC torque control, fast is active, and we're going to estimate resistance by doing a DC current injection at startup. We measure the voltage and then measure the resistance. That's also shown here in this graph here. This is the current flux amplitude and normalized flux, which means flux relative to the value I know it's going to be. The motor has 100% efficiency. The best efficiency is achieved with an RPM of 4,500 RPM. So that's our target speed. Okay, and let's keep in mind that the relationship between torque, low torque, and speed is quadratic. That's what this unit does. Right, we're moving on now, and we start the thing up and look carefully again. And the first thing it does is DC injection, and it measures the resistance. It measures resistance 0.125. And as soon as it's done that, we can then apply a current. And now we have 1 amp. Remember, we are in torque control. And if we look into this unit here carefully, we need to zoom into that. And if we look into that carefully, you will see here the D-axis. And the vertical is the current vector, and the blue one is the voltage. So right now we have a voltage of 2 volts. So we are not using speed control in this case, so we can simply set that to 0. If we now increase the speed, you can see here that the current is not circular because this is a BLDC. And there is a 6 harmonic in the flux locus, which will cause this effect. The torque is now 30 millimeters. The speed is now up to close to 2000. And you will see the voltage increase. If we start increasing it, we are moving up to the speed we want. So now we're looking at 4 amps, 75 millimeters, speed is already there. I can control the direct axis component by negative. Look at that, you see? Controlling it there, you can see the effect on it. There's not much change in the voltage. Field oriented control. If we now increase it to full speed, you simply adjust the tilt, adjust IQ. And moving up, you can see the current increase, voltage increase, up to its maximum. So 7. So there we have maximum volt, 7.3 amps. There's the voltage, about 7 volts. So in conclusion, really, the control we see here of drone control is relatively achievable with this setup. In fact, any type of machine. And it explains quite well. You can have full torque, speed, input power, supply current, and full control of your drone using this approach, and you can therefore be creative with control. Thank you for your attention.